Okay, so the first law of thermodynamics, the total energy of the universe is constant. All right, so I don't see this showing up as a true or false question or a fill in the blank question on the exam. I see it helping us figure stuff out, right? So the total energy of the universe is constant. That means that whatever one thing gains is lost by the surroundings. Okay? Whatever one thing gains is lost by the surroundings. And that's cool because what we can do now is we can say that the change in energy of the system is equal to the negative change in energy of the surroundings, right? And that's what we're going to do. We're going to set up equations like this utilizing the first law of thermodynamics. Okay, so let's consider this a little more deeply. To indicate, first of all, to indicate internal energy, we're going to use a particular symbol. Please go to your book on page 225, and you should be predicting these things as we go along. Page 225. To indicate internal energy, we're going to use the symbol E. Okay? This is very important to help us keep things organized in this chapter because all these terms are going to sound the same if you just throw in letters in there. Okay? All right, so internal energy represents all the energy of the system. All the energy of the system, I'm looking on page 225. The internal energy represents both the kinetic and the potential energy. It's all the energy of the system. Okay? And finally, it's a state function, which means that its value depends only on the state of the system, not on how we got there. Value, you really need to look at this. Open up your book, page 225, and read that. The value depends only on the state, not how we got there. And the picture that's used for that is a mountain. Suppose you've got these mountain climbers, and you've got a person that's climbing up this mountain path. Can you see these people here? It's kind of small. I'm going to make them a little bigger, okay? So you got this guy who's walking up here. He's a little bit skinny. He's really tall. Okay? Knows, so you know which way he's going. He's headed up the path there, okay? Then over here, what you've got a guy on his knees, okay? His nose, okay? Can you see that? Hopefully that's really great. That's really going to help you understand this if you can see these stick figures, okay? A little bit of a torso there, but otherwise he's pretty skinny. Maybe a little bit of hair, not much. This guy's got a flat head. Okay, so eventually this guy is going up the side of the mountain this way. This guy is going up this way. Can you see that? Okay, but once they get up there, they have the same amount of potential energy. Okay, why? Because it is the altitude depends only on the difference between the initial values, not on the path taken. Okay, that's a state function. And the mountain is frequently used when people are trying to identify what's a state function. And the state function, it matters if it's a state function or not because we're going to be comparing energies. And you might be thinking, oh my goodness, we've got these different processes. They're so different. How can we tell? Well, because internal energy is a state function. It doesn't depend on how you got there. It just depends on the overall energy of the system. All right, so look at this. Suppose we've got some substance that we're going to signify as, where am I here? Carbon with a C, okay? And we combine it with oxygen in a reaction called, what do we call this reaction? Carbon and oxygen making carbon dioxide. What do we call that reaction? I'll give you a hint. It ends with ning. Ning. And it starts with burr, right? This is I've lost my vocabulary laughing at my joke. It's burning, okay, which we call combustion, right? It's a combustion reaction. So anyway, we got carbon, we combine it with oxygen, and it's got a certain amount of internal energy. If you were to add up all of the kinetic energies and the potential energies of these reactants, you would find that it has this much energy. Okay? After we burn it, we'll see that the products have this much energy, right? And so let me make some numbers up here, just make it easy to see. Suppose this says, I don't know, let's say 13, and this is 11. Can you see that the difference is the final minus initial, right? Which, if we're putting these numbers in here, are going to be 11 minus 13, which is going to be minus 2, right? And so, if the final is lower than the initial, then the change in internal energy is going to be negative. Can you see that? It's going to be negative. All right. So, as we said before, what energy changes that we have, I know this is repetitious, but it's really important, so I'm hoping that you'll do your best to follow along here. The system, when it loses energy, it's going to go to the surroundings. That's what that's about. Okay, and it's going to lose energy either by doing work on the surroundings or by giving heat to the surroundings. That's how it's going to transfer its energy from the system to the surroundings. And likewise, the surroundings might transfer energy back. In a different reaction, we might have energy that goes from the surroundings to the system. Okay? And that's what it's those energy transformations we're going to be concerned about in these sections. Okay. I think we already said this. Have a look at that. If the energy flows from the system to the surroundings, the change in energy is going to be negative. If it goes the other way, it's going to be positive. From the surrounding standpoint, it's getting energy, right? And so its final is going to be greater than its initial, which is going to make the change in energy positive. And the other way around would be the other way around. Okay, so this is important. Table 6.3. This is not be something you should memorize, but something that's really going to help you think about this. If a system, so we've got some equation, which I don't think I have a slide here for, but it's on page. It's equation 6.4, which is the change in internal energy is going to equal to the heat plus the work. That's a W. That was an ugly W, wasn't it? The heat plus the work, okay? Well, is the heat going to be positive or negative? Or is the work going to be positive or negative? Well, it depends. If the system gains, look at this, if the system gains energy, then this is going to be positive. If the system loses it, it's going to be negative. If the system has work that's done on it, it's going to be positive. And this makes sense, right? Because if the change in energy of a system, if it goes up, well, you'd either have work being done on it or you'd have heat being given to it, right? And so that's what this table means. So the change in internal energy is going to be positive if overall energy flows into the system, and it's going to be negative if in some energy flows out. All right, so let's think about a couple, and we had this I put this in a previous slide. I got these out of order here. Suppose we've got these two suppose we've got these two systems. Okay, just a second here, okay? So these are out of order, I beg your pardon. So we've got this billiard ball, and suppose that this billiard ball is got initially 5 joules of heat. Can you see that? Its initial kinetic energy is 5 joules. I said heat, it's energy. It's got these 5 joules of kinetic energy, and as it goes along, it's losing some energy to the green carpet because of friction. Okay, so it loses half a joule. When it gets there, can you see that it's done work? It's done work on the green carpet. How much? 0.5. And so, I'm sorry, it's lost heat. Forgive me. It's Q. Can you see that? Remember, Q is going to be negative. It's going to be less than 0 if heat is lost, right? And the work is going to be negative, less than 0. It's going to be negative if the system does work on the surroundings, right? So here's the system, right? It's coming along here, and bam, it does 4.5 joules worth of work. Okay? And so it's going to be negative. Can you see that? That's what that negative right there means. Okay? And then if it loses heat by friction, then it's going to be a negative, negative Q. All right? So if the equation we're using here is the change in internal energy is going to be Q plus W, which is equal to minus 0.5, right? Plus minus 4.5 is going to equal to minus 5 joules, right? And that's exactly what we might expect, right? Because if the ball has 5 joules in the beginning and then it's sitting still, it's lost all of them. Lost energy. It's very important that you see that. It can make some very difficult questions easy if you can understand that. All right, so let's consider another set of tables. Let's consider one that's got like a rough carpet on it, okay? So you've got this rough green carpet. As the ball goes along, it doesn't lose a half a joule, it loses 3 joules. So you can imagine by the time the ball gets there, it's going a lot slower, right? So its kinetic energy as it hits the ball is 2 joules because it lost 3 to the table. All right, and so again, delta E is equal to Q plus W. The heat that's lost to the table is 3, so it's lost, so it's minus 3. And the work that's done is minus 2, right? Which is still going to equal to minus 5 joules because it had 5 joules in the beginning. 5 joules, and it has 0 joules here, right? And it lost them. That's what that's about, okay? Joules are lost. And so let me go back and look at that previous equation now. That the change in energy of the system is equal to the negative of the change in energy of the surroundings, right? So the surroundings in the case of this pool table, the surroundings are the green carpet and the purple ball, right? Okay, so finally, let's look at this. A potato cannon, it provides a good example of heat and work. I have no idea why they would put this in a college textbook because this is an accident waiting to happen, right? A potato cannon provides a good example of heat and work associated with a chemical reaction. A potato is stuffed into a long cylinder that's capped on one end and open at the other. Some kind of fuel is introduced in the potato at the capped end, usually a small hole, and ignited. The potato shoots out of the cannon. So far, this is just blah, 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 right? It doesn't help us, but we're about to get to some numbers here, okay? Watch this. If the burning of the fuel performs 855 joules of work on the potato and produces this much heat, what's the change of the fuel, okay? So fuel goes to burned fuel, right? And it looks like it says it produces work 855 joules, but it's done by the system, right? I'm sorry, yeah, it's done by the fuel. So it's going to be minus 855 joules because it's work done by the fuel, right? Okay. And then also it looks like it produces 1422 joules of heat, right? But it's negative because it produces. Okay? And so delta E then is going to be Q plus W, which is equal to minus 1422 plus minus 855. I can't do that in my head. Joules, 1422, 855, 772. So it's 22 equals 2277 joules. But wait a second, let's see this. What is the change in internal energy? Aha, it doesn't say how much is being done by the fuel. It says what is the change. And so it's going to be minus 2277 joules. And that's the answer, minus 2277 joules. Okay, so you have to watch this. What is the change in internal energy? This stuff right here is going to dictate whether we've got positives or negatives. I think, the positives and negatives are one of the biggest challenges here in this chapter. It's going to take some practice. You have to make a guess, and then evaluate your guess and see what's going on. See if you understand it correctly. All right, I think that's it for this.